won't work, but hang on, let me just turn that message off. Which is a report on various bits of joint work with Nathan Broomhead, Raquel Coelho-Simoes, and David Pauksztello and John Wolfe. So I want to quickly sketch the sort of how the theory of projective-minded objects has developed in the past 20 years, before indicating what's happening with simple-minded objects, which are the ones I'm interested in at the moment. So let's start with a recap of projective-minded objects. Is my writing big enough to see on your screens? Yeah, I assume I will get complaints if not. So let me give you an overview of the object, its name, the homological property. Let me try and spell that correctly. Determining it, the generating condition we require, and does it have a theory of mutation? So the starting point is projective objects themselves. So we start with projective objects. The homological characterization of projective objects themselves are inherent homological definition, but it's the X functor in, say, some abelian category A vanishes for all non-zero extensions. And the generating property we want is that for all object A in A, there's a projective cover. So this in add P. So I'm going to think in small world here, but you could take projective covers in a big world if you want. And there's no real mutation theory for such objects. We can generalize this to tilting objects. These objects characterize derived equivalences, so this is where they first appeared. They take the X non-vanishing condition inside a triangulated category D, and so they imitate this condition, but locally just for the object T, so it looks locally like a projective object, and the generating condition is similar to this one, but it's the whole of D can be generated by T as the thick subcategory generated by T, which has a nice presentation of the union over, let me write curly T, I less than or equal to J of this star product where X star Y is equal to the set of objects D in D, such that there's a triangle, such that there exists a triangle with this guy in X and this guy in Y. So we can build D in this nice way, where T, curly T is add of T. Unfortunately, again, there's no mutation theory. So the next generalization, so this goes back to Ricard and Keller. The next generalization is silting theory. Oh, silting objects, let me write. So this goes back to Keller and Vosik, and in its modern form, Ihara and Iyama. And here we take the same generating condition, and we call it M not T. But we only, well, there's the same homological property, sorry, but we don't require negative extensions to vanish, just the positive extensions to vanish. Again, we're in a triangulated setting. And we take the same generating property like this, where curly M is add M, and the point here is we finally can say yes to something. There is a mutation theory. So in some sense, it's not the reason they were first introduced. The reason they're first introduced is they prioritize the algebraic T structures inside your derived category. But one motivation for introducing them can be they close the closed tilting objects under mutation. And there's some mutation theory, and tilting objects are closed under this. You lose this property, but you keep this property when you mutate. At the same time, there's a parallel development based on tilting objects, which is cluster tilting objects. And this typically takes place in the W Calabi-Yau category when W is bigger than or equal to 2. And this was first introduced by Bowen, Marsh, Wright, and Reinecker and Todorov. And here it's suited for the Calabi-Yau case in the sense that we wrap around with the X vanishing condition. So we require only X from X1 up to XW minus 1 to vanish. Again, D is triangulated. And we take again this thick generating condition, but we can write it more succinctly. It's C star sigma C up to sigma W minus 1. C, where C is at C again, and again we have a mutation theory. And one way you can kind of think of this is that cluster tilting theory is the shadow of silting theory in an appropriate quotient. I won't get too much time to talk about this feature in the theory, but it's there. Okay, so that's the development of the theory of projective-minded objects over the last 20 years in a very quick summary. So I want to do the same thing for simple-minded objects to explain the context we fit in. So we know that simple-minded objects, we know what simple objects are. They are objects which have no non-trivial subobjects. But in a triangulated category, this definition makes no sense because all monomorphisms are split. So the idea of a subobject is not very useful inside a triangulated category. And the insight, I think, originally coming from Stefan Koenig and his collaborators, is that one can characterize these things homologically as well, with two classic theorems. So I'm going to ask for mutation. Okay, so simple objects. Typically in a Abelian category. So the S contained in A in a Abelian category. Well, the first homological property we come across is hom A ST is equal to, I'm going to work over an algebraic closed field to make my life simple today. K if S is isomorphic to T and 0 otherwise. So Schur's lemma is the classic theorem. And then we have a generating condition, which says that A equals filt S. Sometimes write it in angle brackets, meaning the extension closure of S. So all the objects which have composition series with composition factors in S. Well, that's the Jordan-Holder theorem. So the generating condition is the Jordan-Holder theorem, and the homological property is Schur's lemma. I'm going to say we have no mutation theory here. Okay, so these give us the things that we can generalize. So I'm going to leave a bit of a gap here to simple-minded collections. So again, this is now, so I would now abbreviate these to SMCs. And here we take Schur's lemma as our homological property, and we take a derived category version. I put 2 here, but I don't want to. Derived category version of the Jordan-Holder theorem, which is, let's say, S, this thick S, which is equal to the union of I bigger than or equal to J now, the shift of I, extension closure of S, down to shift J, extension closure of S. So we have a derived version of a Jordan-Holder theorem, and then there's an extra condition in homological conditions, which is that there are no morphisms from positive shifts of the simple-minded collection to the simple-minded collection. So hom sigma SS, sigma greater than 0 as S equals 0. And this was implicit here. So 2 is implicit. Because we have X less than 0, SS equals 0 in any abelian category. So that was invisible to us at the abelian level, but you can see it at the triangulated category, but it was already there. Okay. And here we do have a mutation, well, let's say sometimes. So this is the point of this talk. Sometimes. I want to explain the sometimes. There seems to be a gap here. And then the Calabi-Yau analog of this is the notion of a W simple-minded system. So for W, so I call it S, and W is going to be bigger than or equal to 1, and this is for a minus W Calabi-Yau category. And here we have the same conditions, so still Schur's lemma. We have negative Hom vanishing, but this time again, liking in the cluster category situation, we only have partially because there's not enough space in the category. So from W minus 1 down to 1, shift of that SS vanishes, and we still have the thick generating condition. But this time again, like in the cluster category situation, it's a finite one. And here we can say yes for the mutation theorem. So we have one generalization going here, another generalization going here. So let me explain this sort of the homological setups that these generalize. So the thing you should have in mind for, let's call this star and this double star. So in star, what we're really looking at is a abelian length category. Length just means the Jordan-Holder theorem holds. S equals simples of H. H, I'm used to calling it H for heart. We get A embedded in its bounded derived category, and we're looking at what happens, sort of a homological characterization of a set of simples of an abelian length category inside its bounded derived category. So the simples essentially go to the SMC. And for the second generalization, the other kind of abelian triangulated category that occurs in representation theory is the stable module category. So I take mod lambda finite dimensional symmetric algebra in this case. So I want it to become Calabi-R. I take S to be the simple modules, and the construction I'm getting takes mod lambda to its stable module category, mod lambda, and sends the simple modules to the non-projective simple modules are one SMS, or simple-minded system. Okay. Want to make one final note in this case. If S is an SMC, we have, but D is the extension closure of S. So I'm going to write this in a slightly sloppy way. It's built like this. If I take this part and this part, I get, let's call this XS and this YS. XS, YS is a bounded T structure in D. Okay, which means 1 from XS, YS equals 0. 2, the shift of XS is contained in XS, and the shift inverse of YS is contained in YS, and 3, D is XS star YS. Okay, so this will be relevant later. Any questions at this point? Okay. So this is the history. You see where it comes from. So think simple-minded collections are simple objects in hearts of bounded T structures whose hearts are length, and simple-minded systems are the non-projective simple, the images of non-projective simple objects in stable module categories. And what I want to explain is this sometimes here and this yes here. So that's the purpose of this talk. And contrast this with what's happening in the projective case where both answers were yes. Okay, so this tells you that something is slightly different, doesn't quite work as nicely in the simple-minded case. So projectives are simpler than simples. Okay. So the first question I want to ask is, when does an SMC mutate? So the question is, I start off with an SMC, when can I get, or when do I do a simple-minded mutation and get a new SMC? Is it always possible to do this? So the setup I'm going to take is, so D is going to be triangulated category. Try and write it properly. D triangulated category. I'm going to assume it's Hom finite and Kroll-Schmidt. And again, this will be the shift. And inside D, I'm going to take T and SMC. And S contained in T, a subset of T may be empty and may be T, so any subset. And the right mutation is obtained as follows. I'm going to discuss right mutation today. In general, in analogy, there's also left mutation. So if I take an object T in T, but it's not lying in S, I take a minimal right extension closure of S approximation of the shift of T. So I take that and I spit out a cone, which I call RS of T, which is its right mutation. Okay, so what does a right approximation means? It means that when I apply the functor from S blank to this morphism here. Let's call this alpha t. So S blank alpha t from this guy. Sorry. From st. Should have extension closures here. Is a surjection. And it's minimal such, so there are no superfluous summands. I'm not going to give a formal definition of minimal. So let me give an example. Classic rep theory example, type A3. So let me draw quickly the bounded derived category, or a part of bounded derived category of the type A3 quiver. So that's the module category. Now I take the shift of the module category with the connecting homomorphisms. And I want to take the negative shift. Lose track of where I am. It should be sigma minus 1 of 1. Sigma minus 1 of 1, 2. Sigma minus 1, 1, 2, 3. Connecting homomorphism. Sigma minus 1, 2, 3. Sigma minus 1, 2. Sigma minus 1, 3. So that's enough to illustrate this. So let me just take T to be the set of simples. 1, 2, and 3. And I'm going to take S to be the simples 2 and 1. The extension closure of S is the additive subcategory with these indecomposable objects. So this is the extension closure of S. So the only simple not in S but in T is the simple 3. That lands over here. And the minimal approximation is from this object 1, 2, and the cone is this guy. So the new simple-minded collection I get, so this is RS of 3, and the new simple-minded collection is 1, 2, and shift of 1, 2, 3. You might notice that this is moved in the wrong way, or seems to be in the wrong position. In order to be compatible with silting mutation, I need to take the shift of this back. So I need to take sigma minus 1 of 1, 2, sigma 1, 2, 3. So the Koenig-Yang mutation will pick out these 3 simples. But notice, in order to do this, I needed to be able to do this step here, take a minimal right S approximation. Okay. The schematic for this picture is, so maybe I'll do that afterwards. Let me just give this lemon. Oh, no, I give the schematic. So the schematic for this picture is, here's my derived category. Here's my Ewing category A. Here's the positive shift of A. And here's the negative shift of A. Written the wrong way if you're used to the hereditary case, but this is the natural homological way. Inside here, I have a torsion theory, T star F. This torsion class is going to be the extension closure of S. And what I do is I take the negative shift of the torsion class here, this, and this is the new category. Okay. So let me call this K equals. So I can think of this mutation operation either as mutation or haplobright and Smilo tilting. And I get the same answer when I take the simples in that module category or in that viewing category. The reason why this works is the lemma by Dugas, which says that if, so he actually says something more general this, so this is a specialized version of Dugas's lemma. If T contained in D is an SMC and S is contained in T, then the extension closure of S is functorally finite in A, which is the extension closure of T, so in the heart A. So in particular, this implies that T equals TF given by extension closure of S, A intersect the right perp of S, and also I'm not going to give it a name because I'm not going to use it today because it corresponds to the other mutation. Left perp of S intersect A, extension closure of S, are torsion pairs in A. Okay, so what does this say? He says that any object of A admits a right approximation from the extension closure of S and a left approximation from the extension closure of S. So you can always define this HRS tilting from an extension closure of a set of simples. Okay, so you can always tilt. So this is the right simple tilt at S. Notice because it's going, this is the torsion class and you're moving right. So that's how you remember this. This would be going this way, so moving left. That's the left simple tilt at S. Okay, so HRS tilting is always defined, but this is a functorial finiteness condition in A. This mutation was taking place in the shift of A. So we need to understand the connection here. And this is our first theorem. This is with Nathan Brumed, Raquel, me, and John Wolf. Okay, so if A is a length heart, I'm gonna switch to using H, otherwise I'll get confused. If H is a length heart with simple objects, T.
So, David?
Yeah.
A question about the lemma, sorry. The functorial finiteness implies that the existence of approximation, but what about the minimality?
Minimality I'm dealing with by, I've put myself in the home finite quotient category, so existence of approximations is enough to get existence of minimal approximations. So that's built into the setting. But if I'm not working in that setting, then I would have to work harder.
Yes, thank you.
Thank you. Yeah, that was a good point. I kind of brushed over this. So thanks for asking this. Okay, so H is length heart with simple objects T, i.e. H is the extension closure of those simples T. And I take S contained in T, a sub collection, and I take T equals TF, the associated torsion pair as defined here. Then the following conditions are equivalent. One, that K, which is this tilt, is a length heart. So this guy here in the schematic is a length heart. This is equivalent to each object in the shift of T without S admits a right S approximation. Again, the co-Smith setting saying the existence of right is sufficient to get minimality. So this is a length heart if and only if you can do this mutation. The third condition is that you can do the mutation. The right mutation S of T exists and is an SMC with the extension closure. I should take the negative shift to be compatible with the Koenig-Yang is equal to K. And then an interesting one from our perspective, which is why we were asking the question in the first place, is if the number of simple objects, isoclasses of simple objects, is finite, then the above are equivalent to a statement in terms of stability conditions. So statement 4 is there exists a stability condition sigma equals ZP. I'll say in a moment what this means, with P naught 1 equals H. P of 1 equals the extension closure of S, and P of naught up to phi put square brackets. So half open, half closed interval is equal to H intersect S perp, that's F in the torsion pair, for some phi strictly between 0 and 1. Okay, so you can characterize this. And so what this is saying, so this is essentially saying there is no gap between the slices. Oh, there exists a stability, sorry, let me write again. There exists a stability condition with a gap between the slices. That's a necessary and sufficient condition to be able to tilt and get a length heart. Okay, so I'm going to say a couple of remarks on this. 1 implies 2. So this is essentially implicit in Dugas. This theorem is Koenig-Yang. And going back up here is essentially uses a lemma of Dugas. So the message here is most of this part of the statement was actually scattered across the literature, but hadn't been assembled. But so this is a complete characterization of it, which was more or less already there. This part, in terms of stability conditions, is new. So let me briefly explain what this part means here. So stability, a brief recap of stability conditions. So a stability function on the abelian category H is just a group homomorphism from the Grothendieck group of H, which will be, in this case, because it's an abelian category, length abelian category, finitely many simples, this is just a free group on the number of simples. Free abelian group on the number of simples. With the property that if I take some object in H, here by abuse, I identify H with its class. This lies in the upper half plane containing the negative real axis, not containing 0, not containing the positive real axis. So in this part of the complex plane. Okay. So we have this. And then, okay, so we write for each H, we write ZH in its modulus argument form. So MH e to the I pi phi of H. This guy is the mass. We're not really interested in it. This guy here is called the phase. And this is what determines semi-stability. So H is semi-stable. If and only if, definition. For all, we're in an abelian category here, so this makes sense. For all non-zero subobjects of H, the phase of H prime is at most the phase of H. And we write P of phi to be the category of semi-stable objects of phase phi. And if H is the heart of a bounded T structure, we can extend to D using shift. So a stability function, sigma Z, so stability condition Z is a stability function and a heart on, and a heart and a stability function on it, which can also be written in terms of this P, which is called the slicing. Here, P of 0, 1. Sorry. P of 0, 1 is the heart, because all of these phases is in this part, so it goes between, it's normalized. So it goes between 0, the phase goes between 0 and 1. So P of 0, 1 is the heart. So that's this condition. So saying the stability function, stability condition with this heart, sorry. And it's called a stability function if a stability condition, if it satisfies two further properties. One is Z satisfies the Hn property, which says that every object can be built out of semi-stable objects. This we get for free if H is length, so we can forget this. And the other condition is Z satisfies the support property. This is a technical condition. I don't want to go into it, but it has an important consequence. So as a consequence of this, which is if I take P of I, which is the extension closure of P of phi, such that phi is in I, this is some interval in the real numbers. If the length of that interval is strictly less than 1, then P of I is length. It's a length abelian category. So the support property says that if you have any P of I where I is length quasi-abelian category, says that these slices give you something which has simples and a Jordan-Holder property. So let me give an example illustrating this. So the example written in different language. So it's originally due to Koenig and Yang. I'm taking a dual of this example because they chose left mutation and we chose right mutation. So, oops. So here I'm going to take this to be the bounded derived category of the nilpotent representations of the quiver with two vertices and one loop, one arrow, no relations. So the nilpotent representations here has two simples. A simple at 1 and a simple at 2. And the claim is, so this is a nice algebraic category, it's a nice length category. If I take K, F star, negative shift of the simple, a shift of extension closure of a simple S1, and F is then the orthogonal of H, so I should say H is the category of nilpotent representations, then K is not length. So I can do the tilt, but I can't do the mutation. So I want ZP with P of 1, it's the extension closure of S1, but I want to break the other properties. So anything with this is going to, so I need this to happen in order to get this. And what I'm going to show you is the other property here. So we're going to have a stability function satisfying this, and I'm going to show it can't possibly satisfy that. So none of these exist. So without loss of generality, I can act with the C action on stability conditions. So I can assume that this is normalized to -1. Okay. And I can choose Z of S2 such that phi of S2 is less than or equal to, is bigger than 0 and strictly less than or equal to 1. So the situation I have here is, here's my negative axis, here's Z of S1, and I can put Z of S2 anywhere here. And any choice of Z, so in the finite length case, stability conditions are determined by their action on the simples. So placing Z of S1 here and Z of S2 here completely determines the stability condition. So this is, I just have two parameters, one of which I'm fixing because I want this condition to be true, and I have complete freedom to do this. The only thing that I could do to kind of break this is to put this also down on this axis, but then I would have the whole of H on the negative real axis, which I don't want. So I'm going to define a module, nilpotent representation Mn with composition series S1 n times and S2 at the bottom. So think about this as the one which goes around this loop n times and then finally makes its way to 2. Okay. One sees here, so the group homomorphism property of a stability function says that in order to work out what Z of Mn is, then I just add together m times Z of S1 and 1 of Z of S2, meaning that I'm going to end up getting Z of, try to use that in a different color, somewhere going up here. And as you see, as n gets really big, the gradient of this line is getting flatter and flatter, meaning that it's tending towards here, never quite reaches here. And then if we look at the submodules here, if I remove one thing from the top, I make the gradient bigger, and so on, each time getting bigger. So all of the sub-objects of this have bigger slope. So this tells us that Mn is semi-stable. But the limit of Zmn as n goes to infinity, sorry, I want the limit of the phase, is equal to 1. So that tells us that I'm not finding my gap here. This requires, so this has no morphisms, so I should point out, because it has a 2 on the bottom, this is in F, which is S1 perp intersect H. So this lies in F, and I can always find a phi which is closer to 1 for each case, which is still in F, meaning that I cannot get this situation. So there is no stability condition with a gap between the slices satisfying this condition. So the resulting mutation cannot be length. Okay. So I think that's quite a nice situation. Okay, so that explains why mutation isn't always possible. So I want to finish with a slogan. Which is mutation as reduction. Okay. So I'm going to have two different setups. The SMC setup, which is I take S contained in D, satisfying the homological, but not necessarily the generating properties of an SMC. And I'm going to assume that S is covariantly finite in the left perp of S and is contravariantly finite in the right perp of positive shifts of S. I'm going to assume that every object in D is bounded with respect to S. So that means that for D in D, if I shift D far enough, or S far enough, I can't see D. So that's sufficiently small and sufficiently large. So eventually I cannot see D if I shift enough. And then finally, I take Z to be a double perpendicular category, so the right orthogonal to negative shifts, including 0 of S and positive shifts of S. So this is where any complement of your simple-minded collection have to lie. They can't have any morphisms to objects in S or negative extensions with S. So this is where your complements have to lie. So given this setup, I'm going to state a theorem, but I want to give the corresponding SMS setup and state the theorem for both collections simultaneously. So S now satisfies the homological properties of a WSMS, but not necessarily the generating. And we're going to assume, firstly, that S is closed under sigma minus W boldface S. This is the Serre functor. And the extension closure of S is functorially finite. So this is actually a necessary condition to be part of a simple-minded system. If you don't have this, then you cannot possibly be part of a simple-minded system, because any extension closed subcategory of extension closure of a subset of a simple-minded system is functorially finite. I should say here in D. And then I have Z, which is the Calabi-Yau orthogonal. There's D and D such that from sigma to the I SD equals 0 for I equals W, 0 up to W. So I've got two different setups, one for SMCs, one for SMSs. The SMS setup is just the wrapped up version of the SMC setup. The functorial finiteness here gets split into two conditions in the two orthogonals here, but the reason it's functorially finite here is the wrapping around forces these guys together, and the Z is just a wrapped up version of this guy, and it doesn't make sense to talk about finite or far enough away shifts, because everything is in somehow finite distance from S anyway in the SMS setup. So this is automatically satisfied. So the two conditions are essentially, two sets of conditions are essentially the same. And the theorem, this is due to Raquel Coelho-Simoes and myself, says that Z is a triangulated category with shift functor let's call it angle brackets 1 from Z to Z, given by I take an object of Z and I shift it. So for Z in Z, I take the right approximation, I spit out the cone, I declare that to be the shift, and I get this. And what you should notice is that this is the mutation triangle. This is exactly the same as what we did here. So it's the same, it's exactly the same recipe. So the recipe for mutation is actually the recipe for producing the shift in this triangulated category Z. So let me finish the statement of the theorem, and then I'll finish by explaining how this is related to mutation. Moreover, there's a bijection between the set of SMCs or WSMSs, depending on the context you're working, in D containing S and SMCs or WSMSs, again, depending on the context, in Z. So there's a bijection between SMCs or SMSs in D containing S and just plain SMCs, SMSs in Z. And the consequence of this is you get from this, provided those SMS setup and SMC setup always hold. The SMS setup always holds when you're starting with something which is a subset of an SMS. It doesn't always hold when you're starting with a subset of an SMC, because we have a counterexample from stability conditions, but this explains what mutation is, and it's similar to the cluster tilting case. Well, what do you do? Well, let me take this. Oh, no, I'm going to take SMCs or WSMSs in D containing S. Well, this is in bijection with, so I'm going to start tautologically with WSMSs, with SMCs or WSMSs in D containing S. Okay, that's the same set on both sides, but the maps are actually the mutation maps. So the mutation maps provide mutually inverse bijections between these sets, provided these setups happen. The theorem that I just stated tells you that you have this bijection between SMCs. I should have not given full credit here. So this is the SMS version. And it's for Hybogin, the SMC version. Sorry about that. We have these bijections from the theorem, and there's a bijection here simply for right mutation doing the shift and for left mutation doing the inverse shift. So what is the mutation? It's reduce, shift, lift. So mutation is just shift in the reduced category. So this gives you a conceptual explanation of why mutation always happens for WSMSs and why these conditions actually turn out always to be the case for finite dimensional algebras. So it explains to you why this always works, that you have simple-minded collection mutation for finite dimensional algebras. Notice in my counterexample, I had to leave the world of finite dimensional algebras, went to nilpotent reps of this infinite dimensional algebra. Okay, I was going to explain a little bit more on the conceptual explanation of Koenig-Yang mutation compatibility, but I was a bit overambitious in what I wanted to cover, so I think I'll stop here. Thank you very much.
Thank you, David, for your very nice talk. Are there any questions or comments? Maybe I start with some question. David, is there some invariant for drive equivalence, and mutations? Because in general case for the stable category, we know that there is a invariant for the SMS. If you have a SMS and have a stable equivalence, then again we have a SMS in the new algebra. And is it possible to say something? At least for example, for self-injective algebra, such that the mutations also invariance under the drive equivalence?
I haven't thought about it. It's a good question. I haven't thought about this. I expect one could say something like this. Could have some compatibility with derived equivalence or stable equivalence.
Because in some sense, maybe it is connected to the Auslander-Rayton conjecture and used this reduction for answering in some cases, at least, the Auslander-Rayton conjecture.
That's kind of the hope for this, but we haven't made too much progress in that direction. What this kind of tells you is, so maybe it doesn't quite work because it's a transitivity type argument, right?
Mhm.
So what you know now is that any SMS that you can reach via mutation necessarily has the same number of objects.
Yeah, this is also the problem, yeah.
But then you have the question of, can you reach all of the SMSs by iterated mutation?
Yes.
Um,
I think these two questions are very important in this direction.
yeah. And that's not clear. Probably I think there are counterexamples in the cluster theory where you have where mutation is not transitive in cluster tilting. So I would expect in general mutation of SMSs is not transitive, but it probably is going to be transitive in the module, so in stable module categories, I would guess, which is the also underwriting conjecture. It essentially should be the also underwriting conjecture, but it becomes a transitivity problem. Yeah.
So any other question, comments? So if not, let's thanks David again. Thank you, David, for your very nice talk. And if it is possible, please send me this a slide for putting on the web page of the conference.
Yeah, I can send these straight away.
Thank you.
Okay. Thank you very much. Okay. The meeting is still being recorded.
Oh, yes, sorry. Maybe I should stop the recording.